Okay, so 6.5, we're going to start looking at triangles. How many people have done like sine, cosine, Sohcahtoa, that kind of stuff? Yeah, if you've done Sohcahtoa, that's basically what this section is. There's a few other things as well. All right, so we're going to be studying specifically right triangles. So first thing, somebody tell me, what is a right triangle? What does that mean? Yeah?
Triangle with one angle that is 90 degrees.
Right, triangle with exactly one 90-degree angle. Could it have two 90-degree angles?
No.
Why not?
Because that would equal 180. That has to be the equal of all the angles in the triangle.
Right, all the angles have to add to 180, so if two of them do, then the sides wouldn't meet. Okay, the side that's across from the right angle, the longest side, does anyone remember what you call that? The hypotenuse. How about the two short sides? The legs. Yep.
Oh, that was a guess.
Well, you were right. So the hypotenuse is the long side, two other sides are the legs. Here's a diagram showing what I just said. Usually when we label the sides of a triangle, we use the English lowercase letters, A, B, C. A and B are usually the legs and C is the hypotenuse. You don't have to do it that way, but that is the way most formulas, especially when you look at Pythagorean Theorem, that's the way it works. This angle in the lower right and the one at the top are both acute angles. Why does this angle and that angle, why do they both have to be acute? We kind of already touched on that.
Because if they're more than 90, it would be more than 180 degrees.
Right. We've already used up 90 for the right angle, so the other two angles have to both be less than 90. Or it wouldn't add up to 180. Notice I wrote here that an acute angle does have to be greater than 0. There's no such thing as a negative angle in a triangle. We can talk about negative angles on a circle by looking at clockwise or counterclockwise direction. But in a triangle, nope, always positive angles. A theorem that we'll use quite a bit when we work with right triangles, the Pythagorean Theorem. And a lot of people remember it that way, but the theorem really is leg squared plus leg squared equals hypotenuse squared. Call the legs anything you want. Okay? But if you call the legs A and B and the hypotenuse C, that's what the Pythagorean Theorem looks like. Questions on that? This theorem can only be used on right triangles. If you had a triangle like that, you cannot use Pythagorean Theorem on that kind of problem. Eventually we'll talk about how you would do stuff with that, but for now, we're going to stick with right triangles. Okay, so I think we've already gone through what the six trig functions are. Okay, we've done the sine, the cosine, the tangent, secant, cosecant, cotangent. The first time we looked at them quickly, we did them on a unit circle. I think we did something like sine was y, cosine was x, and tangent was y over x. Does that sound a little familiar? Yeah. Well, we're going to look at the definitions again, but now we're going to use the words opposite, adjacent, and hypotenuse. So this is a different way to define the six trig functions. So the trig functions are ratios. They're fractions. What's on the top and what's on the bottom of each fraction? A side, a length. So a trig function is a ratio of two lengths. Which lengths you use controls which function you're working with. If you take the opposite length and divide by the hypotenuse length, that's your sine. If you take the length of the adjacent divided by the hypotenuse, that's your cosine. and then the length of the opposite divided by the length of the adjacent, that's your tangent. Now, the nice thing is once you know the 3 on the left, you automatically know the 3 on the right. Does anybody remember what you do with each function on the left to get the one on the right? You flip it. So cosecant would be hypotenuse over opposite. Secant is hypotenuse over adjacent. And cotangent, adjacent over opposite. So what I focus on is the ones on the left. Those are the ones that are most important. And if you remember those, just think in your head, flip, and you have all the ones on the right. And we mentioned it earlier, but can somebody tell me what's the trick? There's like a word or I guess it's kind of like an acronym. Yeah, Sohcahtoa. And what does that stand for? Let me just put it right here. How does that help you to remember it? Yeah.
So it would be, it's pretty much sine opposite over hypotenuse.
Yeah, so the sine is the opposite over the hypotenuse. Yep.
Pretty much follows through, but the other one is cosine, adjacent hypotenuse.
Yep, cosine would be adjacent over hypotenuse. And the last one?
Tangent. Opposite adjacent.
Opposite over adjacent. So reading down kind of tells you which one is which. So if you can remember that, that'll kind of help you. And then remember, flip them, and that gives you all the other ones. Okay, so Sohcahtoa. Okay. Hypotenuse is a term that where it is in the triangle, it never changes. It's kind of like if I said, where's up? For everybody in this room, up is the same way, towards the ceiling. But opposite and adjacent are kind of like left and right. They're relative. So what I mean by that is it's not the same. It depends on your perspective. So for me, left is the door and right is the window. For you, that's the opposite. So in a triangle, when you're dealing with opposite and adjacent, you can't ask me where's opposite and where's adjacent in that triangle. I can't tell you. You haven't given me a perspective to look at it from. If you said, okay, you're going to look at it from that perspective, now I can tell you that's opposite because it's the side that's furthest away, and adjacent is always the side that's right next to it. That's adjacent. Hypotenuse, I could answer that question just by knowing where the 90 is. Hypotenuse, always across from the 90. Now, same type of sketch. This time I'm going to say you're standing down there. Well, if you change the angle you're referencing, pretend like you're standing in a new spot on the triangle, that's like changing the direction you're facing. Now opposite and adjacent switch. Opposite is always the side furthest away. Okay, opposite is the side that if you got rid of it, you'd still have that angle right there. I can erase this side, and I still have an angle. Okay, adjacent is the side that if you got rid of it, because it's right next to the angle, you don't have an angle there anymore. You just lost one side of your angle. And then hypotenuse. So hypotenuse is the only thing that never changes. It's always across from the 90. Any questions on what I mean by opposite and adjacent being relative? All right, so let's suppose we had two right triangles. And the angles are the same. Does that mean that they are exactly the same size? No. They could be similar, but they could be different sizes. And that's important to understand that if you said, okay, I have a triangle with a 45, a 45, and a 90. And I said, you asked me, how big is it? Well, it could be any size you want. You could have 45, 45, 90 that big, or that big. Those triangles are similar. The angles are exactly the same. And the reason that's important, I'm going to show you right now. So when you do right triangle trig, the size of the triangle doesn't really matter. If you're dealing with two triangles that are similar, meaning all the angles are the same, and I ask you to find one of these six trig functions, you can use any size triangle you want, and you'll still get the same answer. Let me show you. Here's two similar triangles. They're both 30, 60, 90 triangles. The first triangle has legs of 1 and root 3, and the hypotenuse is 2. And then in the second triangle, it's twice as big. The legs are 2, 2 root 3, and 4. Okay, let's find, let's just pick an angle. Let's pick the 30. Okay, and let's find the sine of it. Let's find the sine of 30 in the small triangle, and then we'll do it in the big triangle, and see, do we really get the same answer? Now, I could have picked any trig function. I could have picked the cosine, I could have picked the tangent, it doesn't matter. And I could have picked the 60. I just chose the 30. Can somebody remind me, what's sine? It's what divided by what?
Opposite divided by hypotenuse.
Opposite divided by hypotenuse. So, Mallory, what's the side opposite 30 in the triangle on the left? 1. Yep. And Casey, what's the hypotenuse of the triangle on the left? 2. So using the small triangle, the sine of 30 comes out to 1/2. Okay, we could double check that if we wanted. You could type it in, sine 30, just change to degrees, and you'd get 1/2. Let's just double check we did it right. Sine of 30, 1/2. Okay, let's try it in the bigger triangle. How about, Brandon, what's the side opposite the 30-degree angle in the bigger triangle?
Sine 2.
Yep, 2. And Wyatt, what's the hypotenuse in the bigger triangle? 4. So when I found the sine of 30 in the bigger triangle, did I get the same answer? Dave?
Yes.
Yeah, 2/4 is the same as 1/2. Okay, so the point, the sine of 30 is the sine of 30 no matter what size triangle you're working with. The sine of 30 is always 1/2. Big triangle, small triangle, doesn't matter. Okay. Questions on that idea? So, what we're going to have, okay, in a second, is a problem like this. They're going to tell you the sine of theta is 5/6. They're going to give you one of the 6 trig functions. Using that one, I want you to figure out all the other ones. But I have to give you at least one. Okay, so how do you do that? Well, first of all, if they're giving you sine or cosine or whatever, they're giving you 2 of the sides. Right? As long as you know the definition, that's one side, that's another side. So we're going to take the information they're giving us and use it to label two sides of a triangle. And now, in a right triangle, if you know 2 out of 3 of the sides, how can you get the third one? Think about Kevin?
Pythagorean Theorem.
Yeah. Once you know 2 sides, use the Pythagorean Theorem. That gives you the third side. Now you can find anything you want. Okay, so take what you're given, make a diagram with those 2 numbers, use the Pythagorean Theorem to get the third side. And you don't have to write the last sentence, but now you can find, you know all the sides, so you can find anything you want. Okay, so let's look at this one. Okay, so first one says the sine of theta equals 5/6. Just move these out of the way. Okay, so first thing I'm going to do is just identify the 2 sides they're giving me. So Hannah, what 2 sides are they giving me there?
Opposite and hypotenuse.
Yeah, they're giving me the opposite and the hypotenuse. How long is opposite?
5,
And the hypotenuse?
6.
Okay, so we're going to set up a diagram with what she just said. Draw a triangle, make the opposite side 5, make the hypotenuse 6. It doesn't matter where you put the angle. Put it at the top, put it on the right. It doesn't make a difference. Just put it somewhere. Okay. If I put it at the top, Calvin, where is the opposite side?
The bottom.
The bottom. Opposite hypotenuse. All right, and now to get the third side, how about Colleen? What theorem do I use to get the third side?
I can't say it.
Can't say it?
No.
What does it begin with?
P.
P, yeah, Pythagorean Theorem. So we're going to use that, and you're going to get the third side. You can label this side whatever you want. Call it A, B, doesn't matter. Michael, could you set up the Pythagorean Theorem for me with what I've got right there? What's that? Do you remember the Pythagorean Theorem from geometry?
Yeah.
So that's what we want to do, is just fill those 3 things into that theorem. Dave, can you help him out?
A squared plus b squared equals c squared, so we do a squared plus 5 squared equals 6 squared.
So a squared plus 5 squared equals 6 squared. Okay, go ahead and square everything that you need to. So we get a squared would equal how much? How about Josh? What would a squared be?
Well, 36 squared could be.
Oh,
30 squared.
squared.
Oh. Yeah, I know. Kind of. 11.
11. So a squared is 11, but that doesn't mean this side is 11 units long. What do we do to get rid of squaring? Square root it. Just leave it like that, square root of 11. Okay, so now I'm going to label that square root of 11. Now I'm going to go through and write all 6 trig functions. Sine, I already know, 5/6. So you don't need to write that one down. Cosine. about AJ? What's the definition for cosine?
Opposite over adjacent, right?
That's tangent.
Adjacent over hypotenuse.
Adjacent over hypotenuse. Adjacent is square root of 11. Hypotenuse is 6. You don't do anything with that. You leave it just like that. Tangent. That's the first one that he said. Opposite over adjacent. That one you cannot leave like that. What's wrong with tangent? Right, we don't want to leave the square root in the bottom, and we've had things like this before. Multiply top and bottom by the square root, and you get 5 root 11 over 11. There's your tangent, your cosine, and your sine. Now, to get the other three, what am I going to do with all of those? Just flip them. So the cosecant is 6/5. The secant is going to be 6. Right, it's going to be 6 over square root of 11, so it's kind of like the tangent. We're going to have to fix it. 6 square roots of 11 over 11. And now the cotangent, well, you could flip one of two things. You could have flipped this, or you could flip the final answer. Which one would be easier to flip here?
The first one.
The first one, because if you flip it, the root goes to the top and you're done. So it's square root of 11 over 5. If you flip the second one, that's fine too. You're going to have to fix it again, and you're going to get square root of 11 over 5. So those are the 6 trig functions. Questions on how we got those? Okay, so that's one way they could give you a problem, like that. Second way, they give you a diagram. Without figuring anything else out here, can somebody tell me which trig function do I have enough information to find with just what's right there?
The hypotenuse.
Well, I could find the hypotenuse, but without finding it, I know I know 2 trig functions. I know tangent, and that means I also know the cotangent. So if I want to start with that, Andrew, what's the tangent?
5 over 12.
5 over 12, yep. And if we know that one, then the cotangent. Josie, what's the cotangent? 12 over 5. Now, if they want anything else, which they do, we gotta find the hypotenuse. Curtis, to find the hypotenuse, how would I do that?
A squared plus b squared equals c squared, so it would be 25 and 144 equals, it's a big number, 169.
Yeah, yep,
Square root of that.
yep. So it would end up being 13.
That works.
So if you go through the Pythagorean Theorem, you get a nice answer, which means we're not going to have any roots in the bottom. Okay. If you didn't get a nice answer, like on the last problem, leave the square root. Don't put decimals for this kind of problem. All right, so now let's go through the rest. Sine. Cameron, what's my sine here?
5 over 13.
Yep, 5 over 13. Julia, how about my cosecant? So do you remember what we do to the sine to get the cosecant?
Yeah, 13 over 5.
You just flip it, yep. And Braden, what about my cosine?
That's 12 over 13, right?
Yes, adjacent over hypotenuse. And And then the last one, my secant, Kelvin.
It would be 13 over 12.
13 over 12. Yep. So when we did this problem, we didn't actually figure out how big any of these angles were. All we did was find out a bunch of stuff about the angles. Okay, the sine of the angle, the cosine of the angle, and so on. Eventually, though, we're going to ask the question, well, how big is that angle? 12 degrees, 100 degrees, how big is it? Okay, but not yet. Okay, any questions on that? Okay, so let's go through 6 trig functions of 45. I want to do this one because you've seen these numbers before. Okay, what's the first thing I have to do, or that I should do? Because they want me to find all 6. I don't have enough information right now. Yeah, find the hypotenuse. And what would the hypotenuse be here?
It'd be 2 squared.
4? 2 squared?
2 squared. Yeah.
4.
Oh, no.
2 squared would be 4. But no, it's not 4.
I'm not 2 squared, I mean square root of 2.
Square root of 2. Yeah. Now, they want us to look at the trig functions from the perspective of the 45-degree angle. So, does it matter which 45-degree angle I pick? No. Okay. Pick either one. Let's look at it from the perspective of that one. Okay. It's not going to matter because these other 2 sides are the same. So you're going to get the same answer. So let's start with the sine. Miley, what's my sine? One over 1 would be the tangent. 1 over square root of 2. Yep. So I'm just looking. Let's put it up. So we get 1 over the square root of 2. And Casey, when I fix that, what would I get?
You'd multiply the top and bottom by square root of 2. And you get the square root of 2 over 2.
Yep. Square root of 2 over 2. Now, to find the cosecant, just take that and flip it. I would flip the first one because the square root would go to the top. Square root of 2. Okay. Any questions on the first 2? Caitlin, how about the cosine? Caitlin, help her out. What's the definition for cosine?
Adjacent over hypotenuse.
Adjacent over hypotenuse.
So it'd be the same thing as sine.
It's the same thing as sine because the opposite and adjacent are the same. Well, if the sine and cosine are the same, so are the cosecant and secant. Okay, and lastly, the tangent. What's my tangent?
It would be opposite over adjacent.
Mhm.
So
1 over 1, which is just 1. Flip it, 1. So finding the trig functions for 45, very quick. Because you get a lot of simple numbers and then numbers that you keep. Alright, this one. Use that diagram to find the 6 trig functions of 30 and 60. So we're going to do two problems. Well, first of all, when we did trig functions, what kind of triangle did I say we always have to work with? We're doing a right triangle. Is that a right triangle? No. What kind of triangle is it? It's equilateral. Okay? Keep that in mind. Is there a way that I could make that into a right triangle somehow?
they all have to be the same angles, right?
For equilateral, they're all the same angle, yes. So I can actually, that's a good point. Why don't we put that in right now? All those angles are 60. But how could I make a right triangle out of that? Yep.
You could like put a line down the middle and split one angle in half.
Right. If you put a line exactly down the middle, it does exactly what Ian just said. It splits this angle at the top in half. So now that's a 30. And it's a 30. And that's exactly the angle we need to do the problem. So we just got lucky by doing that. It works. Okay. So let's take this triangle. Move it off to the side. And Curtis, how long is the hypotenuse in that red triangle?
It'd be 2. Right?
It's 2, because it's the side of the equilateral triangle. Any other side that I know the length of? Yeah?
Well, the bottom has to be 1.
Right, because we bisected that side. That's a theorem from geometry. If you draw in an altitude, it not only bisects the angle, it bisects the side at the bottom. So each side is 1. And now, to get the last side, what could I do? Yeah.
The theorem, I can't say it now.
The Pythagorean Theorem. So if you go through and do it, that's what you'll get. Anybody need me to go through the theorem to get that? Okay. Right, now it's just a matter of filling in all 6 trig functions. Okay, let's start from the perspective of, let's do the 30. So I'm going to start by looking at it from there. Okay, when we do the 60, then we're going to switch opposite and adjacent. Okay, so sine of 30. Brandon, what's the sine of 30 here?
It would be 1 over 2.
Yep, 1 over 2. Wyatt, my cosine of 30?
It would be 2 over. I don't know.
Do you remember what's the definition for cosine again? Adjacent over hypotenuse. So what side is adjacent? What side is right next to the 30? Square root of 3 over 2. And tangent? Michael, what's the tangent of 30?
1 over the square root of 3.
Yep, 1 over the square root of 3. And with any square root, I need to fix it. Can't leave that in the bottom. So Colin, what do I get when I fix that?
Square root of 3 over 1.
Not square root of 3 over 1. We'll get square root of 3 over 3. Okay, so there's my first 3. Now, what are we going to do with all of those? Flip them. Okay, so just cosecant. That's quick. We get 2. Secant.
2/3.
Careful, we've got a square root in there. Can anyone tell me what you get when you flip it and fix the root?
2 square root of 3 over 3.
Yes, 2 square root of 3 over 3. And then the last one, square root of 3. How do you think all these answers are going to relate to when we do 60 degrees? Yep.
As cotangent, 0 over 1.
Yes. Square root of 3. Thank you. How do you think all these answers are going to relate to when we do the 60-degree angle? They're what? What do you mean opposite?
It's going to be like a cosecant. It's going to be like the sine. but like for the other one, right? Like wouldn't like the sine be like 2? And
Yes.
then the other one would be 1/2, but it's for the 60 instead.
Right, so what's going to happen is they're going to switch places.
Yeah.
All these numbers are going to move around, but they're all going to be the same numbers. So, for the sine of 60, now you're looking at it from that perspective. Pretend like you're standing down by the 60. Opposite is square root of 3. Adjacent is now 1. Okay. Hypotenuse, well, hypotenuse didn't change. Okay? But that's the labeling if you look at it from the perspective of the 60. So let's go through. Sine is opposite over hypotenuse. Okay, let's see. Cosine is adjacent over hypotenuse. So 1 over 2. And tangent, opposite over adjacent. Square root of 3 over 1. So things switched places, but I don't think they switched places exactly like we said. Let me do the other 3, and then I'll circle what switched places. Cosecant is 2 root 3 over 3. Secant, we're going to flip it and get 2. Okay, I'm going through it quick because we just did all these numbers. Cotangent is going to be root 3 over 3. So let's zoom out and see what switched places. Let's try that. So the sine and the cosine switched. Those two switched places, going from 30 to 60. The cosecant and the secant, those two answers switched places. And then the tangent and the cotangent, those two numbers switched places. So if you look at those boxes, that's what switched. And if you read off the names of them, just look at how you pronounce them. Sine, cosine. Secant, cosecant. Tangent, cotangent. So what ended up switching is all the functions with the word co in front. Okay? And the fancy name for that is cofunctions. Everything that you see a box around, that's a pair of cofunctions. So that's what happens with the 30 and the 60. Any questions on that? Let's see. This I think we've already talked about a couple times. It says that the two small angles in a right triangle always have to add up to 90. Why?
Because the total sum of the triangle has to be 180.
Exactly. We've already talked about that a couple different ways. Okay. Two small angles in a triangle are always, in a right triangle, are always complementary. Okay, so here's the diagram that we're going to use to solve a right triangle. That's how you label everything kind of generically. On the sides, we always use English letters, A, B, and C. But for the angles, we're using Greek letters. Does anybody know the name of either one of those Greek letters?
I don't know what to say here.
No? Josh, you think you know?
No, I don't.
You're not sure?
Yeah, I'm not sure. I don't know.
How about, they're the first two letters in the Greek alphabet. Alpha and beta. And when you set it up, you always have to set it up so A is across from alpha and B is across from beta. You can draw the triangle flipped, reflected, any way you want. But if you sketch it and you label that side as A, you have to put alpha across from it. Wherever you put B, put beta across from it. How come not just use like capital letters and lowercase letters? I think, yeah, that could be confusing because if you ask me a question and you say, well, how did you get B? I'd have to be like, well, do you mean capital B or lowercase b? Which one? Also, certain letters can look the same. So if we start getting into using capital and lowercase, especially like the letter C, capital C, lowercase c, that could look the same. So if we use Greek letters, there's no question. Greek letters are angles, English letters sides. All right, let's take that and just practice this. What's the sine of alpha in that picture?
A over C.
Let's see. Sine is opposite over hypotenuse. Yes. A over c. Okay. Now I'm going to do something, and I want you to see if you notice what happened. Let's find the cosine of theta. What's the cosine of beta? It's the same thing. Adjacent over hypotenuse. A over c. Let's do one more. Let's do tangent of alpha. Okay, what's the tangent of alpha?
A over B. Or, yeah.
Tangent would be opposite over adjacent, so it's A over B. Now let's find the cotangent of beta. I'm not just picking random things. Once I pick something on the left, I'm picking a certain thing to go with it on the right. So let's see what happens here. Hannah, what's the cotangent of beta?
B over A.
What's our definition for cotangent?
Adjacent over opposite.
Right. So from here, what side is adjacent to that?
B.
No, B is across from it.
A.
So A.
B.
So yeah, A is adjacent over, you said opposite,
Yeah.
and opposite is
B.
B. So A over B. How does the cotangent of beta and the tangent of alpha compare?
They're the same.
They're the same. Okay. Sine, cosine. Tangent, cotangent. There's the pattern to what I'm picking. Okay. And the pattern is summed up very briefly in that theorem. It says that if you have co-functions, like sine, cosine, tangent, cotangent, any of those ones I put boxes around, so take any pair. If you have co-functions of complementary angles, you always get the same answer. Okay, let's look back at what I had. I already went through sine, cosine. Those are definitely co-functions. Alpha, beta. Those are complementary. Why are they complementary? We just answered that question right there. Because they're in a right triangle. So if you've got co-functions of complementary angles, the answer comes out the same. So, let's look at something numeric. What's the co-function that goes with sine? The one we put a box around. Cosine. And what's the complement of 20? 70. Sine and cosine are cofunctions. 20 and 70 are complementary. Therefore, those two things are equal. What are they equal to? I have no idea. But I know whatever the sine of 20 is, the cosine of 70 comes out exactly the same. Some random decimal. But they are the same random decimal. Any question on that? So where would we use that? Right here. Okay, so on this kind of problem, I'd ask you to simplify and then probably explain how you got your answer. Okay, what are the two functions I have here? Just name them. What are they?
Sine.
Sine. Yep. Cosine. What are sine and cosine? They are
No. Oh wait, yeah.
Yeah, they're complementary, right? Are they the ones-
the functions, the name.
Oh, cofunction.
These are co-functions. And then what about 35 and 55?
They're complementary.
They are complementary. So this theorem applies. Cofunctions of complementary angles are equal. So what does that mean you'd get when you subtract?
0.
You get 0. If you're trying to figure out, well, what's the sine of 35, you're thinking about it the wrong way. I have no idea what the sine of 35 is. I have no idea what the cosine of 55 is. I don't. But I know they're the same. And in math, if you subtract two things that are the same, you get 0. That's it. Let's try this one. Okay, so now I have tangent and cotangent. Are those cofunctions? Okay. Yep. How about 20 and 70? Are those complementary? Yes. So I'm really dividing two things here that are the same. I have no idea what the top is, no idea what the bottom is, but I know they're the same. So what do I get? I get 1. That's where you use this idea. If you change this problem to the tangent of 21 divided by cotangent 70, you can't do it. Not without a calculator. Any questions on that one? Would that idea work for addition? If you add two things that are the same, do you always get the same answer? No. Subtraction, it works, but it doesn't work for addition. Addition, you get the thing doubled. How about multiplication? No. If you divide two things that are the same, you always get 1. If you multiply two things that are the same, you get that thing squared. So it doesn't work for that. Yeah, that's a good place to stop. Okay, so homework tonight's on 361. You've got about 20 minutes. You can get a little bit of a start on that. Okay. On 1 through 14, that's all. 16, 18, and 21 to 23 is all. Make sure you copy these last two. Sine of 40 over cosine 50, and tangent 35 minus cotangent 55. So tomorrow we'll finish 6.5 tomorrow, and then on Thursday we'll look at section 7.2. Yes?
So those two are just extra questions.
These are also questions to do, yep. So do everything in the book and then do the two that I wrote below. So.